Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the moon's deepest secrets. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The moon hangs above tonight, as it has for countless evenings, a pale disk suspended in darkness. Most nights, few pause to consider what they observe. The surface appears solid, familiar, unchanging. Yet this celestial companion harbors mysteries that challenge every assumption about its nature, its birth, and its relationship to the world beneath our feet. Each crater tells a story spanning billions of years. Each shadow conceals processes that shaped not only the moon itself, but the very conditions that allowed life to flourish on Earth. Scientists measure the moon's diameter at 3,474 kilometers, roughly 1/4 the width of Earth. This ratio makes our moon the largest satellite relative to its parent planet in the solar system, excepting Pluto and Charon, which some consider a binary system rather than a planet and moon. The moon's mass equals 1/81st that of Earth, enough gravitational influence to raise ocean tides twice daily and gradually slow our planet's rotation. Over geological time, this tidal friction has increased the length of Earth's day from perhaps 6 hours in the early solar system to the current 24-hour cycle. The moon's face shows patterns visible to the naked eye, features that have inspired mythology across every human culture. Telescopes reveal a surface scarred by impacts, marked by the circular remnants of ancient collisions that occurred when the solar system was young and chaotic. The dark patches, called maria or seas, contain no water despite their names. Early astronomers designated these features believing them to be actual oceans, vast bodies of water that might harbor life. Instead, they represent plains of solidified basalt, volcanic flows that filled enormous impact basins between 3.2 and 3.8 billion years ago. The lighter regions, the lunar highlands, consist primarily of anorthosite, a rock type rich in the mineral feldspar. These elevated areas represent the moon's original crust, formed as lighter minerals floated to the surface of a global magma ocean. The composition tells a story of differentiation, the process by which heavier materials sink toward a planetary body's center while lighter components rise. This same process occurred on Earth, yet the moon's version proceeded more rapidly due to its smaller size and faster cooling rate. What remains deeply puzzling is the moon's very existence in Earth's orbit. Most planets in the solar system either possess many small moons, typically captured asteroids and debris, or no moons at all. Mars has 2 tiny, irregularly shaped satellites that are almost certainly captured asteroids. Jupiter and Saturn host dozens of moons, ranging from massive Ganymede and Titan down to small rocky fragments. Earth's single, disproportionately large satellite suggests an unusual formation process that scientists have struggled to explain for decades. The moon's composition resembles Earth's mantle more closely than typical meteorites or other solar system bodies, hinting at a shared origin between the two worlds. Chemical analysis of lunar samples reveals nearly identical isotope ratios for oxygen, titanium, and other elements when compared to Earth rocks. This similarity suggests the moon formed from Earth material, not from independent accretion in the early solar system. Yet, the Moon notably lacks the iron-rich core expected from standard planetary formation processes. Its core comprises only about 2% of its total mass, compared to roughly 30% for Earth. Only recently have scientists begun to appreciate how cosmically strange this Earth-Moon arrangement truly is. The Moon influences Earth's climate through tidal effects on both oceans and the solid planet itself. It stabilizes Earth's axial tilt, preventing the dramatic oscillations that would otherwise occur due to gravitational perturbations from other planets. Without this stabilizing influence, Earth might experience chaotic variations in its orientation relative to the Sun, making stable climate conditions far more difficult to maintain over geological time. Some researchers suggest complex life might never have evolved without the Moon's moderating presence. The Moon's surface experiences temperature swings that would instantly kill any terrestrial organism. Sunlit areas reach 127 degrees Celsius, hot enough to boil water, while shadowed regions plunge to minus 173 degrees Celsius, colder than liquid nitrogen. No atmosphere exists to moderate these extremes or to redistribute heat from day to night sides. The boundary between light and shadow on the lunar surface, called the terminator, represents one of the most extreme temperature gradients in the solar system, with differences of 300 degrees Celsius occurring across distances of mere meters. This airless environment preserves the Moon's surface features with remarkable fidelity. No weather patterns disturb the ancient dust. No erosion wears away crater walls or fills impact basins. The footprints left by Apollo astronauts between 1969 and 1972 will persist for millions of years, preserved in the vacuum like fossils pressed into stone. Each bootprint represents a human moment frozen in geological time, destined to outlast civilizations, mountain ranges, and perhaps even the species that created them. The Moon's apparent simplicity masks layers of complexity that continue to challenge scientific understanding. Its phases result from changing illumination angles as it orbits Earth, yet the mechanics of its formation, the source of its unusual composition, and the precise timing of its evolutionary history remain subjects of active research and considerable debate. What appears as a familiar, constant presence in Earth's sky carries within its rocky interior the keys to understanding planetary formation, the early solar system's violence, and perhaps even the origins of life itself. The ancient surface waits in silence, holding its secrets beneath layers of pulverized rock and cosmic dust, accumulated grain by grain across billions of years of patient bombardment. 4.5 billion years ago, the young solar system churns with violence. Planetesimals career through space, colliding and accreting in the gravitational dance that will eventually produce the familiar worlds of today. Earth exists, but not as the blue marble suspended in photographs from space. Instead, it resembles a molten hellscape, its surface a sea of magma heated by constant impacts and radioactive decay. No oceans exist. No atmosphere capable of supporting life wraps the planet in protective layers. Only rock and metal, fire and vacuum in the endless ballet of early planetary formation. In this primordial chaos, a Mars-sized body approaches Earth's orbit. Scientists have named this hypothetical impactor Theia, after the Greek Titaness who gave birth to the moon goddess Selene. Theia measures perhaps 6,000 kilometers in diameter, roughly half Earth's width, but massive enough to possess its own gravitational field and internal differentiation. Like Earth, Theia has developed an iron core surrounded by a silicate mantle. Its trajectory carries it inexorably toward a collision that will reshape both worlds beyond recognition. The impact occurs at a glancing angle, striking Earth's surface at approximately 45 degrees and a velocity of 40,000 kilometers per hour. The collision releases energy equivalent to billions of nuclear weapons detonating simultaneously, vaporizing both impactor and a significant portion of Earth's outer layers. Temperatures at the impact site exceed 7,000 degrees Celsius, hot enough to melt rock instantly and convert solid matter into plasma. The force of the collision tilts Earth's axis to its current 23.5-degree inclination, establishing the seasonal cycles that will later prove crucial to the development of complex climate systems. Most of Theia's iron core merges with Earth's core, sinking toward the planet's center under gravitational force. However, the collision ejects enormous quantities of vaporized and molten material into space, creating a disk of debris that extends thousands of kilometers from Earth's surface. This material, heated to temperatures that would boil metals, begins to cool and condense in the vacuum of space. Gravity gradually pulls the dispersed matter together, forming clumps that collide and stick together in a process called accretion. Within perhaps a century, remarkably rapid by geological standards, this debris disk consolidates into a single large body, the Moon. The newly formed satellite orbits at a distance of only 20,000 kilometers from Earth, roughly 1/16 its current distance. At this proximity, Earth appears enormous in the lunar sky. Subtending an arc 16 times larger than the Moon appears from Earth today. Tidal forces between the two bodies are correspondingly intense, raising solid rock tides hundreds of meters high on both worlds. The evidence for this giant impact hypothesis lies hidden within the chemical composition of lunar samples. Apollo astronauts returned 842 pounds of moon rocks to Earth between 1969 and 1972, providing scientists with direct access to lunar material for the first time in human history. Laboratory analysis reveals that Earth and Moon rocks share nearly identical isotope ratios for elements including oxygen, titanium, and silicon. This similarity suggests the two bodies formed from the same source material, supporting the idea that the Moon originated from Earth's mantle rather than forming independently elsewhere in the solar system. Yet mysteries persist in the isotopic record. Some elements show subtle differences between Earth and Moon samples, hinting at incomplete mixing during the collision process. The Moon's depletion in volatile elements, those that vaporize easily at high temperatures, suggests formation under conditions hot enough to drive off water, carbon, and other compounds essential to life. This chemical signature provides a fingerprint of the extreme temperatures generated during the Theia impact. Temperatures so intense they selectively boiled away the lightest components while preserving heavier elements in the condensing lunar material. Computer simulations of the giant impact struggle to reproduce all observed characteristics of the Earth-Moon system simultaneously. Models that generate a moon with the correct mass and orbital properties often predict chemical compositions that don't match laboratory measurements of lunar samples. Conversely, simulations that accurately reproduce the Moon's chemistry frequently produce satellites that are either too small, too large, or orbiting at incorrect distances. This mismatch between theory and observation suggests that scientists' understanding of the impact process remains incomplete despite decades of research. The timing of the collision also raises questions about early solar system dynamics. Some researchers propose that Theia originated in one of the Lagrange points, gravitationally stable regions where objects can orbit the Sun in sync with Earth. Under this scenario, Theia and Earth shared the same orbital path for millions of years before gravitational perturbations from other planets destabilized the arrangement and sent the smaller body careening toward collision. Only took 40 million years or so to fundamentally reshape both worlds. Alternative theories attempt to explain the Moon's origin through different mechanisms. The fission hypothesis suggests that Earth spun so rapidly in its early history that centrifugal force ejected material from the planet's equator, material that subsequently condensed into the Moon. The capture hypothesis proposes that the Moon formed independently elsewhere in the solar system and was later captured by Earth's gravity. However, neither alternative adequately explains the chemical similarities between Earth and Moon rocks or the system's unusual angular momentum distribution. The giant impact hypothesis, despite its remaining uncertainties, provides the most comprehensive explanation for the Moon's existence. It accounts for the satellite's large size relative to Earth, explains the similar chemistry of terrestrial and lunar rocks, and predicts the system's total angular momentum. Most importantly, it situates the Moon's formation within the broader context of late heavy bombardment, the period of intense impacts that sculpted all inner solar system planets during their first several 100 million years. The collision's effects extend far beyond simply creating Earth's satellite. The impact likely stripped away any primordial atmosphere that had accumulated around early Earth, resetting the planet's atmospheric evolution and potentially delaying the development of conditions suitable for life. The debris disk created by the collision may have shielded Earth's surface from subsequent impacts for thousands of years, providing a brief respite in the otherwise violent environment of the early solar system. The Moon retreats. Each month, each year, each millennium, Earth's gravitational companion moves farther away, stepping backward in a cosmic dance that has continued for billions of years. The mechanism appears deceptively simple tidal friction. Earth's oceans rise and fall twice daily in response to lunar gravity, creating bulges of water that travel around the planet as it rotates. Yet the Earth spins faster than the Moon orbits, causing these tidal bulges to lead the Moon's position slightly. The gravitational pull of these offset water masses tugs the Moon forward in its orbit, gradually accelerating the satellite and forcing it into higher, more distant paths around Earth. Currently, the Moon drifts away at a rate of 3.8 centimeters per year, roughly the speed at which human fingernails grow. This measurement comes from laser-ranging experiments that began in 1969 when Apollo astronauts placed retroreflectors on the lunar surface. Scientists at observatories around the world fire laser pulses at these mirrors and measure the time required for light to make the round trip. The precision astounds researchers can determine the Earth-Moon distance to within millimeters, revealing not only the Moon's gradual retreat, but also tiny variations in its orbital velocity and the slight wobbles in Earth's rotation. The implications of this recession extend far beyond simple measurement. As the Moon moves away, its gravitational influence on Earth weakens proportionally to the square of the distance. Tides become smaller. The Moon appears smaller in the sky. Earth's rotation slows less rapidly than it did in the past. When the Moon orbited closer and exerted stronger tidal forces, scientists calculate that when the Moon first formed, perhaps 20,000 kilometers from Earth's surface, tidal forces were so intense that both bodies remained molten for millions of years, constantly flexed and heated by gravitational stress. Ancient rocks preserve evidence of this changing relationship between Earth and Moon. Tidal rhythms leave signatures in sedimentary deposits, creating patterns of alternating thick and thin layers that reflect the varying strength of tidal currents over time. Geologists have identified these rhythmites in formations as old as 2.5 billion years, providing direct evidence of lunar distance and Earth's rotation rate in the deep past. The rocks reveal that 900 million years ago, a day lasted only 18 hours, and the Moon appeared significantly larger in Earth's sky. Some of the most remarkable tidal records come from the Wheelie Wally Formation in Western Australia, where 2.45 billion-year-old banded iron formations display cyclic patterns linked to ancient tidal cycles. Each band represents thousands of years of deposition. Yet the overall pattern reflects the monthly cycle of spring and neap tides. The preservation of such delicate timing across geological eras demonstrates the Moon's consistent influence on Earth's surface processes, even as the satellite's distance and strength have changed dramatically. The Moon's recession rate has not remained constant throughout geological history. During the Precambrian, when most of Earth's surface was covered by shallow seas, tidal friction was less efficient than today. The current rate of 3.8 centimeters per year represents an unusually rapid recession, accelerated by the particular configuration of modern ocean basins. The Atlantic Ocean, in particular, has dimensions that resonate with tidal frequencies, amplifying the dissipation of tidal energy. Only took the breakup of Pangaea and the opening of the Atlantic to transform Earth into a more efficient tidal break. Computer models attempting to trace the Moon's orbital evolution backward in time encounter a significant problem. If the current recession rate remained constant throughout Earth's history, the Moon would have been touching Earth's surface only 1.5 billion years ago. Yet, geological evidence suggests the Moon has influenced Earth's tides for at least 3.8 billion years. And formation models place the satellite's origin at 4.5 billion years ago. This timing discrepancy, known as the lunar distance paradox, indicates that tidal friction operated differently in the past. Several factors could explain the paradox. Early Earth's rotation rate was much faster, completing a full revolution in perhaps 6 hours rather than 24. The faster spin would have reduced the efficiency of tidal energy dissipation, slowing the Moon's recession. Additionally, the configuration of continents and ocean basins has changed dramatically over geological time. Different arrangements of land and sea would have altered tidal patterns and the rate at which tidal energy converts to heat through friction with the sea floor and coastal margins. The Moon's retreat also affects its apparent size as viewed from Earth. Currently, the Moon's angular diameter varies between 29.3 and 34.1 arc minutes, depending on its distance at different points in its elliptical orbit. By cosmic coincidence, this range closely matches the Sun's apparent diameter of 31.5 to 32.5 arc minutes, enabling the spectacular solar eclipses that have captivated human observers throughout history. However, this remarkable correspondence is temporary. In approximately 600 million years, the Moon will appear too small to completely cover the Sun's disk, ending the era of total solar eclipses on Earth. Future projections of the Moon's orbital evolution suggest it will continue retreating until tidal forces lock Earth's rotation to the lunar orbital period. At that point, billions of years in the future, the same hemisphere of Earth will always face the Moon, just as the same hemisphere of the Moon currently always faces Earth. The day and month will have identical lengths, perhaps 47 current days long. Tidal friction will cease, and the Moon's distance will stabilize at approximately 560,000 kilometers, roughly 1.5 times its current orbital radius. The mathematical precision of tidal mechanics reveals itself in the Moon's influence on Earth's rotation rate. Each century, tidal friction slows Earth's rotation by approximately 2.3 milliseconds, a tiny change that nonetheless accumulates over geological time. Ancient solar eclipses provide independent confirmation of this gradual deceleration. Historical records of eclipses from Babylon, China, and Greece, when compared to modern calculations, show systematic timing discrepancies that match the expected effects of tidal breaking almost exactly. Coral growth patterns offer another window into ancient Earth-Moon dynamics. Fossil corals from the Devonian period, 400 million years ago, display daily growth bands organized into monthly and yearly cycles. Counting these bands reveals that Devonian years contained approximately 400 days, each lasting about 22 hours. The Moon orbited closer to Earth and appeared larger in the sky, raising tides perhaps twice as high as those experienced today. The moon's retreat continues in the present moment, invisible to human perception but measurable with scientific instruments. Each laser pulse fired at the lunar retroreflectors returns data confirming the satellite's steady migration toward the outer solar system. The process proceeds with the inexorable patience of geological time, reshaping the Earth-Moon system at speeds too slow for biological awareness, yet fast enough to significantly alter the relationship between these two worlds over the span of deep time. The early moon glows like a coal pulled from a furnace, its entire surface molten beneath a black sky. No atmosphere exists to scatter light or moderate temperatures. No familiar Maria pattern marks the face that will one day inspire human mythology. Instead, the satellite presents a uniform sphere of liquid rock, heated by the violence of its formation and the constant flexing of gravitational tides from nearby Earth. This is the magma ocean period, a phase in lunar evolution that lasted perhaps 100 million years, when the moon's entire outer layer remained liquid while the interior slowly began to cool and solidify. The concept of a lunar magma ocean emerged from careful analysis of Apollo samples, particularly the light-colored rocks called anorthosites that dominate the moon's highland regions. These rocks consist almost entirely of the mineral plagioclase feldspar, a calcium and aluminum silicate that forms when molten rock cools under specific conditions. On Earth, anorthosites occur rarely and in small quantities, typically associated with layered igneous intrusions or ancient mountain belts. The moon's highlands, however, contain anorthosite in vast quantities, covering roughly 80% of the satellite's surface and extending to depths of several kilometers. Laboratory experiments reveal that plagioclase feldspar crystallizes from basaltic magma at temperatures around 100–200 degrees Celsius, but only when the magma lacks significant quantities of dissolved water or other volatile compounds. The mineral's low density, approximately 2.7 grams per cubic centimeter, causes it to float on denser liquid rock, much as ice floats on water. For the moon's highlands to form through this flotation process, enormous volumes of molten rock must have existed simultaneously across the satellite's entire surface, supporting vast rafts of crystallizing feldspar that gradually thickened into a continuous crust. The magma ocean's composition evolved as cooling progressed. Initially, the liquid contained the mixed ingredients of lunar bulk composition: silicon, aluminum, iron, magnesium, calcium, and smaller quantities of other elements. As temperatures dropped below 100 to 500 degrees Celsius, high-temperature minerals began to crystallize and sink toward the moon's center. Olivine formed first, followed by pyroxene, both dense silicate minerals rich in iron and magnesium. These early crystals accumulated in the lower portions of the magma ocean, leaving the remaining liquid progressively enriched in aluminum, calcium, and silicon. When temperatures reached approximately 100–200 degrees Celsius, plagioclase feldspar began to crystallize in substantial quantities. Unlike the earlier minerals, plagioclase floated upward through the remaining liquid, accumulating at the surface in thick layers. This flotation crust represents the moon's primordial highlands, the light-colored terrain visible through telescopes and preserved in ancient impact basins. The process required careful balance, cooling fast enough to maintain crystal formation, but slowly enough to allow density-driven segregation over millions of years. Beneath the flotation crust, the final stages of magma ocean crystallization produce some of the moon's most unusual rocks. As plagioclase removal depleted the remaining liquid in aluminum and calcium, the residual magma became enriched in incompatible elements, those that don't readily substitute into common rock-forming minerals. This late-stage liquid crystallized into a rock type called creep, an acronym for its enrichment in potassium, K, rare earth elements, Ra, cerate, and phosphorus, P. Creep rocks contain concentrations of uranium, thorium, and other radioactive elements far exceeding typical lunar or terrestrial values. The distribution of creep across the Moon's surface provides clues to magma ocean dynamics. Orbital gamma-ray spectroscopy reveals that creep signatures concentrate on the near side of the Moon, particularly in the region between Mare Imbrium and Oceanus Procellarum. This asymmetric distribution suggests that the magma ocean didn't cool uniformly. Perhaps the Earth's gravitational field affected convection patterns in the liquid rock, concentrating incompatible elements on the hemisphere facing Earth. Only took a few million years of preferential cooling to establish chemical heterogeneities that persist 4.4 billion years later. Isotopic studies of lunar samples reveal another mystery related to magma ocean crystallization. Measurements of neodymium and samarium isotopes in Highland rocks indicate that the flotation crust formed approximately 4.4 billion years ago, within 100 million years of the Moon's formation. However, some Highland samples yield ages as young as 4.2 billion years, suggesting that portions of the primordial crust remained molten or were remelted by later processes. The exact timing and duration of magma ocean solidification remain subjects of active research and scientific debate. Computer models of magma ocean cooling must account for multiple heat sources and loss mechanisms. Initially, the Moon's interior was heated by the accretional energy of the giant impact, gravitational potential energy released as the satellite formed, and radioactive decay of short-lived isotopes like aluminum-26. Heat loss occurred primarily through radiation to space from the Moon's surface, with convection in the liquid rock transporting thermal energy from the interior to the surface. The balance between heat generation and heat loss determined the cooling rate and the sequence of mineral crystallization. The magma ocean's final solidification created the Moon's internal structure. The deepest portions, enriched in iron and magnesium from early crystal accumulation, formed a dense lower layer that may have partially melted again during later bombardment events. The middle layers consist of cumulate rocks formed by the gravitational settling of olivine and pyroxene crystals. The uppermost layer, the anorthositic Highland crust, provides the low-density cap that gives the Moon its overall layered structure and explains why Highland rocks are systematically less dense than Mare basalts. Evidence for the magma ocean hypothesis comes not only from Highland anorthosites, but also from the chemistry of Mare basalts. These younger volcanic rocks, which erupted between 3.2 and 3.8 billion years ago, show chemical signatures indicating they formed by partial melting of magma ocean cumulates. The basalt's enrichment in iron and titanium reflects their source in the deep lunar interior, where dense minerals accumulated during the magma ocean's crystallization. The chemical evolution from primordial magma ocean to later volcanic activity provides a continuous narrative of lunar thermal history spanning over 1 billion years. Modern lunar science continues to refine understanding of magma ocean processes through laboratory experiments, theoretical modeling, and analysis of new data from orbital missions. The Lunar Reconnaissance Orbiter and other spacecraft provide increasingly detailed maps of Highland composition and structure, revealing subtle variations that reflect complex crystallization histories. Each measurement adds detail to the story of the Moon's molten beginning, when an entire world existed as liquid rock slowly cooling beneath the stars, grain by grain, crystal by crystal, building the solid foundation that would support billions of years of subsequent geological evolution. Beneath the moon's familiar face lie hidden masses, concentrations of dense material that pull at spacecraft with invisible fingers of gravity. These gravitational anomalies, called Mascons, short for mass concentrations, lurk primarily beneath the circular maria, the dark plains that early astronomers mistook for seas. From orbit, nothing in the visible landscape hints at their presence. The basalt flows appear uniform, their surfaces marked only by the usual collection of small craters and wrinkle ridges. Yet instruments aboard lunar orbiters detect variations in gravitational acceleration that reveal dense plugs of material buried kilometers beneath the surface, remnants of impacts so violent they fundamentally altered the moon's internal structure. The discovery of Mascons emerged from tracking the orbital paths of early lunar spacecraft. The lunar orbiter missions of the 1960s, designed to photograph potential Apollo landing sites, began experiencing unexpected changes in their trajectories as they passed over certain regions of the moon. Spacecraft would accelerate slightly when crossing Mare Imbrium, Mare Serenitatis, and other large circular basins, then decelerate as they moved beyond these features. The effect was subtle but measurable, requiring constant thruster adjustments to maintain stable orbits. Initially, mission controllers attributed these perturbations to navigation errors or instrument malfunctions. Only careful analysis revealed that the spacecraft were responding to local variations in the moon's gravitational field. Subsequent missions confirmed and refined the Mascon phenomenon. The Apollo Command and Service modules experienced similar orbital perturbations during their lunar missions, requiring periodic engine burns to compensate for the gravitational effects. The Gravity Recovery and Interior Laboratory mission, launched in 2011, provided the most detailed measurements of lunar gravity variations to date. Twin spacecraft flying in formation around the moon detected gravitational changes by monitoring tiny variations in the distance between them as they orbited. The resulting gravity maps reveal Mascons as circular regions of enhanced gravity, typically 200 to 300 kilometers in diameter, centered beneath the largest impact basins. The physical nature of Mascons reflects the violence of basin-forming impacts. When asteroids or comets tens of kilometers in diameter struck the moon at velocities of 15 to 20 kilometers per second, they excavated craters hundreds of kilometers across and several kilometers deep. The impact energy fractured and displaced enormous volumes of lunar crust, creating complex patterns of uplift and subsidence that extended far beyond the visible crater walls. Computer simulations suggest that the largest impacts may have punched completely through the lunar crust, exposing the denser mantle material beneath and allowing it to flow upward into the newly created basins. This process of mantle uplift provides the most widely accepted explanation for Mascon formation. The moon's mantle, composed primarily of olivine and pyroxene minerals, has a density of approximately 3.3 grams per cubic centimeter, significantly greater than the 2.9 grams per cubic centimeter typical of crustal anorthosite. When impact excavation removed several kilometers of low-density crust and exposed the underlying mantle, the resulting gravitational signature became permanently embedded in the moon's structure. Later, volcanic activity filled many of these basins with basalt flows, but the dense mantle material remained beneath the surface, creating the gravitational anomalies detected by orbiting spacecraft. Mare Imbrium presents perhaps the most dramatic example of Mascon structure. This circular basin, approximately 1,200 kilometers in diameter, formed roughly 3.9 billion years ago when an impactor estimated at 60 kilometers across struck the moon's near side. The collision excavated material equivalent to a sphere 200 kilometers in diameter, ejecting debris across the entire near-side hemisphere and creating secondary crater chains extending thousands of kilometers from the impact site. Gravity measurements reveal that the Mascon beneath Mare Imbrium represents an excess mass of approximately 40 billion tons concentrated in a region roughly 300 kilometers across. The distribution of Mascons across the Moon's surface tells a story of preferential preservation. Large Mascons occur almost exclusively on the lunar near side, the hemisphere that constantly faces Earth. The far side, despite containing impact basins of similar size and age, shows much weaker gravitational anomalies. This asymmetry likely reflects differences in crustal thickness between the near and far sides. The near side crust averages 30 to 40 kilometers thick, while far side measurements indicate crustal thicknesses of 60 to 80 kilometers. Impacts on the thicker far side crust were less likely to penetrate completely through to the mantle, reducing the opportunity for dense material to migrate upward and create lasting gravitational signatures. Some Mascons display complex internal structure that hints at the chaotic nature of large impact events. High-resolution gravity data reveals that many Mascons consist of multiple dense regions rather than single uniform masses. Mare Orientale, the youngest and best-preserved large impact basin, shows a Mascon structure with a central dense core surrounded by a ring of lower-density material. This pattern may reflect the complex sequence of crustal collapse, mantle rebound, and volcanic filling that occurred during and after the basin-forming impact. The timing of Mascon formation provides constraints on the Moon's early thermal evolution. Most large impact basins, and their associated Mascons, formed during the late heavy bombardment period between 3.8 and 4.1 billion years ago. At that time, the Moon's interior was significantly warmer than today, making the crust and upper mantle more ductile and responsive to impact-induced stress. The preservation of Mascon structures over billions of years indicates that the Moon's interior cooled and stiffened relatively quickly after basin formation, preventing the gravitational relaxation that would gradually eliminate such density contrasts over geological time. Modern spacecraft missions continue to refine understanding of Mascon structure and origin. The Lunar Reconnaissance Orbiter carries an instrument that measures tiny variations in surface elevation, providing complementary information about the relationship between gravity anomalies and topographic features. Surprisingly, many Mascons exhibit negative topographic signatures. They occur in regions that are slightly lower in elevation than surrounding terrain. This seemingly contradictory relationship between high gravity and low elevation reflects the complex interplay between impact excavation, mantle uplift, and subsequent geological processes. Laboratory analysis of Apollo samples provides ground truth for Mascon interpretation. Rocks collected from the edges of large impact basins contain mineral assemblages and shock metamorphic textures that confirm the extreme pressures and temperatures generated during basin formation. Some samples show evidence of melting and rapid cooling that occurred during impact events, while others preserve fragments of deep crustal or mantle material excavated from several kilometers below the surface. Only took microseconds of extreme violence to create gravitational anomalies that persist across geological eras. The gravitational influence of Mascons extends beyond their immediate locations. Computer models demonstrate that Mascons affect the orbital evolution of natural satellites and artificial debris around the Moon. Small objects in low lunar orbit experience perturbations that can lead to orbital decay and surface impact within months or years. This phenomenon has implications for future lunar missions, requiring careful consideration of Mascon effects in spacecraft trajectory planning and station-keeping operations. Each Mascon represents a frozen moment of cosmic violence, a gravitational fossil preserving the memory of impacts that reshaped the Moon's surface and interior structure billions of years ago. They serve as invisible monuments to the chaotic early solar system, when large projectiles routinely crossed planetary orbits and delivered energy sufficient to melt continents and excavate craters the size of small nations. The Moon presents the same face to Earth across every orbit, a phenomenon so familiar that most observers accept it without question. This gravitational lock, called synchronous rotation, ensures that one lunar hemisphere remains permanently visible from Earth, while the opposite hemisphere stays forever hidden. The mechanism appears straightforward. Tidal forces from Earth's gravity have gradually slowed the Moon's rotation until its rotational period matches its orbital period exactly. Both cycles now require 27.3 days to complete, creating the illusion that the Moon doesn't rotate at all. Yet careful observation reveals that this cosmic dance involves subtle variations, tiny oscillations that allow Earth-based observers to glimpse portions of the normally hidden hemisphere. These oscillations, called librations, occur because the Moon's orbit around Earth follows an elliptical rather than circular path. When the Moon travels closest to Earth, at the point called perigee, it moves faster in its orbit due to stronger gravitational acceleration. However, the Moon's rotational speed remains constant, governed by its own internal angular momentum. This mismatch between varying orbital speed and constant rotational speed creates an apparent wobbling motion when viewed from Earth. As the Moon speeds up in its orbit during perigee passage, it appears to lag slightly in its rotation, allowing observers to see a narrow strip of terrain normally hidden beyond the eastern limb. The opposite effect occurs when the Moon reaches apogee, its most distant point from Earth. Here, orbital velocity decreases while rotational speed remains unchanged, causing the Moon to appear to rotate slightly ahead of its orbital position. This leads the rotation, revealing terrain normally hidden beyond the western limb. The total east-west libration spans approximately 7.9 degrees, enough to expose an additional 7% of the lunar surface beyond the theoretical 50% that would be visible if the Moon's orbit were perfectly circular. Libration in latitude results from the Moon's orbital inclination relative to Earth's equatorial plane. The lunar orbit tilts 5.1 degrees from the ecliptic, while Earth's equatorial plane inclines 23, 5 degrees to the ecliptic due to our planet's axial tilt. The combination of these tilts creates a complex geometric relationship that causes the Moon to appear to nod up and down in the sky over the course of its orbit. Sometimes Earth-based observers look slightly down on the Moon's north pole, revealing terrain in the northern hemisphere normally hidden beyond the limb. 2 weeks later, the viewing angle shifts to expose southern hemisphere features instead. A third type of libration, called diurnal libration, results from Earth's rotation carrying observers to different positions relative to the Moon during a single day. As Earth spins, an observer's viewpoint shifts by up to 6,400 kilometers, Earth's radius between moonrise and moonset. This changing perspective allows glimpses of lunar terrain around the eastern limb when the Moon rises and around the western limb when it sets. Though smaller in magnitude than the other libration effects, diurnal libration contributes an additional 1 degree of apparent motion, adding to the total area of lunar surface visible from Earth. The combined effect of all libration types allows Earth-based observers to see approximately 59% of the Moon's surface over time, significantly more than the 50% that would be visible from a perfectly synchronous satellite. However, the additional 9% appears only in narrow strips along the lunar limb, foreshortened by the acute viewing angle and often obscured by the shadows of crater walls and mountain ranges. These libration zones remained largely mysterious until spacecraft missions provided direct observations of the far side terrain. Historical observations of libration effects contributed to early understanding of the moon's physical nature. Ancient astronomers recognized that certain features near the lunar limb appeared and disappeared with a regular monthly cycle, providing evidence that the moon was a spherical body rather than a flat disk. Galileo Galilei noted libration effects in his telescopic observations of 1609, though he initially attributed them to a genuine wobbling motion rather than an apparent effect caused by orbital mechanics. Only later did astronomers recognize that libration results from the viewing geometry rather than actual changes in the moon's rotational state. The precise measurement of libration amplitudes required centuries of careful telescopic observation. By the 18th century, astronomers had established that the moon's libration followed predictable patterns linked to orbital mechanics, providing early evidence for the gravitational relationships governing planetary motion. These observations supported Isaac Newton's law of universal gravitation and helped refine understanding of the moon's orbital characteristics, including its distance, period, and the eccentricity of its elliptical path around Earth. Modern laser ranging experiments reveal that the moon exhibits tiny additional librations beyond those predicted by simple orbital mechanics. These physical librations result from the moon's slightly non-spherical shape and non-uniform mass distribution. The moon's figure is elongated along the Earth-facing direction, creating a permanent tidal bulge frozen into the solid rock. Gravitational interactions between this asymmetric mass distribution and Earth's gravity field generate small torques that cause the moon to oscillate around its average orientation with amplitudes of several arcseconds. The most significant physical libration has a period of 9 years and results from the interaction between the moon's orbit and the gravitational influences of the Sun and other planets. As Earth's orbit carries the Earth-Moon system around the Sun, changing gravitational forces create subtle perturbations in lunar motion. These perturbations, though tiny, are measurable with laser-ranging precision and provide information about the moon's internal structure, particularly the size and state of its core. The study of librations also reveals details about the moon's moment of inertia, a measure of how its mass is distributed relative to its rotation axis. Analysis of physical libration amplitudes indicates that the moon is differentiated, with denser material concentrated toward its center and lighter material in the outer layers. This evidence supports models of lunar formation through accretion and subsequent melting, which would have allowed gravitational settling to separate materials by density. Libration zones present unique challenges and opportunities for lunar exploration. The constantly changing illumination conditions in these regions create complex thermal environments where temperatures vary more dramatically than in areas that maintain consistent orientations relative to the Sun. Some libration zones experience extended periods of continuous shadow or continuous sunlight, depending on the season and the moon's position in its orbit. These extreme conditions may preserve volatile compounds, like water ice, in permanently shadowed regions while creating harsh thermal cycles in areas subject to variable illumination. The gravitational lock that creates synchronous rotation represents the final state of tidal evolution for most satellite systems. Initially, both Earth and Moon experience mutual tidal torques that gradually synchronize their rotational and orbital motions. Earth's much larger mass meant that lunar tides on Earth were stronger than terrestrial tides on the Moon, causing the Moon to achieve synchronous rotation first, while continuing to slowly decelerate Earth's rotation. Eventually, both bodies will become mutually tidally locked, with the same hemispheres always facing each other, though this process will require billions of years to complete. The Moon's synchronous rotation state, maintained across geological time despite various perturbations, demonstrates the fundamental stability of gravitational interactions in the solar system. Only took a few 100 million years for tidal forces to achieve this lock, yet the system has remained stable for over 4 billion years, since a testament to the inexorable patience of celestial mechanics operating across scales of time that dwarf human experience. In the deepest shadows of the moon, where sunlight has not touched the surface for billions of years, water waits in crystalline silence. These permanently shadowed regions exist at the lunar poles, hidden within craters whose high walls block the low-angled rays of the distant sun. Here, temperatures remain constant at -230 degrees Celsius, cold enough to freeze carbon dioxide and preserve water ice indefinitely against the vacuum of space. The discovery of lunar water ice challenged fundamental assumptions about the moon's bone-dry nature and revealed that our satellite harbors billions of tons of frozen water, delivered grain by grain across geological time by comets and asteroids carrying the remnants of the early solar system's ice and organics. The existence of lunar water ice remained theoretical speculation until the 1990s, when orbital missions began detecting indirect evidence of hydrogen concentrations at the lunar poles. The Clementine spacecraft, launched in 1994, carried a bistatic radar experiment that bounced radio signals off the lunar surface and detected them with antennas on Earth. Areas near the South Pole returned radar signatures consistent with water ice deposits, though the data remained ambiguous and controversial. Scientists debated whether the signals indicated actual ice or simply rough surface textures that produced similar radar characteristics. More definitive evidence emerged from the Lunar Prospector mission, which orbited the Moon from 1998 to 1999, carrying a neutron spectrometer designed to detect hydrogen atoms in the lunar surface. When cosmic rays strike the Moon, they generate neutrons that bounce through the upper layers of rock and regolith. Hydrogen atoms, particularly those in water molecules, efficiently absorb neutrons and reduce the flux detected by orbital instruments. Lunar Prospector data revealed significant neutron absorption near both poles, suggesting hydrogen concentrations equivalent to water ice mixed with the surface material at levels of 1 to 10% by mass. The most dramatic confirmation of lunar water ice came from the Lunar Crater Observation and Sensing Satellite mission in 2009. L-Cross deliberately crashed a spent rocket stage into Cabeus crater near the Moon's south pole, while a trailing spacecraft analyzed the debris plume ejected by the impact. Spectroscopic analysis of the ejector detected unambiguous signatures of water vapor, along with traces of carbon monoxide, methyl, and other volatile compounds. The impact excavated approximately 105 kilograms of water from the shadowed crater floor, confirming that substantial ice deposits exist within the lunar regolith. The source of lunar water ice traces back to the early solar system's population of comets and water-rich asteroids. These primitive bodies, formed in the cold outer regions beyond the asteroid belt, contained substantial quantities of water ice mixed with rocky and metallic components. Gravitational perturbations from the giant planets scattered many of these objects into the inner solar system, where they collided with planets and moons during the late heavy bombardment period between 3.8 and 4.1 billion years ago. Some fraction of the water delivered by these impacts survived in locations where temperatures remained low enough to prevent sublimation back to space. Most of the Moon's surface experiences temperature cycles that would quickly vaporize any water ice exposed to sunlight. Daytime temperatures can exceed 120 degrees Celsius, hot enough to rapidly sublimate ice directly from solid to vapor without passing through a liquid phase. However, the combination of the Moon's small axial tilt, only 1.5 degrees, and the high walls of polar craters creates regions that remain in permanent shadow. These thermal refugia maintain temperatures cold enough to preserve water ice for billions of years, effectively serving as natural freezers that concentrate and store volatile materials delivered from space. Computer models of ice stability on the lunar surface reveal a complex relationship between temperature, time, and the migration of water molecules. Even in permanently shadowed regions, some water ice slowly sublimates and migrates across the surface as individual molecules bouncing from point to point. This process, called ballistic transport, allows water molecules to eventually reach the coldest available locations, typically the floors of the deepest polar craters. Over geological time, this migration concentrates ice in regions with the highest probability of long-term preservation. The Lunar Reconnaissance Orbiter, operational since 2009, has provided increasingly detailed maps of temperature and illumination conditions at both lunar poles. These measurements reveal that permanently shadowed regions cover approximately 13,000 square kilometers at the South Pole and 17,000 square kilometers at the North Pole. Within these areas, the coldest locations maintain temperatures below -240 degrees Celsius, cold enough to preserve not only water ice, but also more volatile compounds like carbon dioxide, ammonia, and methane that require even lower temperatures for stability. Recent analysis of data from multiple lunar missions suggests that water ice concentrations vary significantly both between different craters and within individual shadowed regions. Some areas contain ice mixed uniformly with the regolith at low concentrations, while others may harbor nearly pure ice deposits several meters thick. The South Polar region appears to contain larger and more concentrated ice deposits than the North Pole, possibly due to differences in crater size, depth, and thermal history between the two regions. The discovery of lunar water ice has profound implications for future human exploration of the Moon. Water represents perhaps the most valuable resource for sustained lunar operations, serving not only as drinking water for astronauts, but also as a source of oxygen for breathing and hydrogen for rocket fuel when split through electrolysis. The ability to extract and process lunar water ice could dramatically reduce the cost and complexity of lunar missions by eliminating the need to transport these essential materials from Earth's deep gravity. However, extracting water ice from permanently shadowed craters presents significant technical challenges. The extreme cold makes mechanical systems brittle and electronic components unreliable. The lack of sunlight eliminates solar power as an energy source, requiring either nuclear power systems or complex arrangements to beam power from sunny locations. The low-gravity environment and fine regolith create difficulties for excavation and processing equipment designed for terrestrial conditions. Laboratory experiments with simulated lunar ice suggest that extraction may require heating the ice-bearing regolith to temperatures above -160 degrees Celsius to achieve reasonable sublimation rates. This heating demands substantial energy input, potentially requiring several kilowatts of power to process even small quantities of material. The engineering challenges of operating such systems in the harsh environment of permanently shadowed craters remain subjects of active research and technology development. The isotopic composition of lunar water ice may provide clues to its origin and history. Different sources of water in the solar system, comets, asteroids, and solar wind interactions produce characteristic isotopic signatures that can be distinguished through mass spectrometry. Analysis of water extracted from various lunar locations could reveal whether the ice derives primarily from cometary impacts, asteroid collisions, or ongoing processes like the reduction of oxygen-bearing minerals by hydrogen atoms from the solar wind. Some researchers propose that lunar water ice represents a continuously replenished resource rather than a finite deposit from ancient impacts. Modern comets still occasionally strike the Moon, and the solar wind delivers a steady flux of hydrogen atoms that can combine with oxygen in lunar minerals to form trace quantities of water. These ongoing processes may slowly add to the polar ice reservoirs, though at rates far below those that occurred during the early solar system's bombardment periods. The study of lunar water ice also provides insights into similar processes on other airless bodies throughout the solar system. Mercury's polar regions contain radar-bright deposits that likely represent water ice preserved in permanently shadowed craters, similar to those on the Moon. Asteroids and comets visited by spacecraft show evidence of water ice and hydrated minerals, confirming that water remains common throughout the solar system despite the Moon's reputation as a bone-dry world. Only took 4 billion years of patient accumulation to create these hidden reservoirs, grain by grain, impact by impact, building deposits that may someday sustain human civilization beyond Earth. The Moon possesses an atmosphere so tenuous that for centuries scientists considered it airless. This exosphere, as the wispy envelope is properly called, contains fewer gas molecules per cubic centimeter than the best laboratory vacuums achieve on Earth. Yet, technically, an atmosphere exists a gossamer shell of sodium, potassium, argon, neon, and helium atoms that extends thousands of kilometers above the lunar surface. The density is so low that molecules rarely collide with one another, traveling in ballistic trajectories like microscopic satellites orbiting through space until they either escape to interplanetary medium or impact the surface below. The discovery of the lunar atmosphere began with telescopic observations in the 1980s, when astronomers detected a faint yellow glow around the Moon's limb. This sodium emission, visible only through specialized filters and sensitive detectors, revealed that atoms of this alkali metal surrounded the Moon in a thin cloud. The source of these sodium atoms puzzled researchers initially. The Moon's surface rocks contain sodium in feldspars and other minerals, but liberating individual atoms requires processes energetic enough to break chemical bonds and launch material into space. Micrometeorite bombardment provides the primary mechanism for atmospheric generation. Every second, tiny particles smaller than grains of sand strike the lunar surface at velocities between 10 and 70 kilometers per second. These hypervelocity impacts vaporize both the incoming meteoroid and small quantities of surface material, creating brief plumes of hot gas that expand rapidly into the vacuum. Most of this vapor condenses back onto the surface within minutes, but some atoms acquire enough energy to reach escape velocity and contribute to the sparse atmospheric envelope. Solar wind sputtering represents another source of atmospheric atoms. The continuous stream of charged particles from the Sun, primarily protons and helium nuclei, strikes the lunar surface with energy sufficient to knock atoms loose from the crystal lattices of surface minerals. This process operates continuously on the sunlit hemisphere, gradually eroding the uppermost atomic layers of rocks and soil grains. The sputtered atoms typically have lower energies than those produced by micrometeorite impacts, so more of them fall back to the surface rather than escaping to space. Thermal desorption adds to the atmospheric inventory through a gentler process. As sunrise temperatures heat the lunar surface to over 100 degrees Celsius, weakly bound atoms and molecules sublimate directly from mineral surfaces into the vacuum. This process primarily affects volatile elements and compounds that accumulated in the regolith through previous impacts or solar wind implantation. The desorbed material follows the temperature cycle, rising during lunar day and condensing back to the surface during the 2-week lunar night. The composition of the lunar atmosphere varies with location and time, reflecting the different source mechanisms and the Moon's 28-day cycle of illumination. Sodium and potassium, detected through their characteristic spectral emissions, show enhanced concentrations near the terminator, the boundary between light and shadow, where temperature gradients drive complex circulation patterns. Argon-40, produced by radioactive decay of potassium-40 in lunar rocks, emanates continuously from the interior and reaches peak concentrations during lunar night when surface temperatures drop low enough to prevent immediate escape to space. Apollo missions provided the first direct measurements of atmospheric density through instruments deployed on the lunar surface. The Apollo 17 Lunar Atmospheric Composition Experiment detected argon, neon, and helium at concentrations roughly 1/1,000,000th those found in Earth's atmosphere at sea level. Subsequent analysis revealed that most of the detected gases originated from the Apollo spacecraft themselves, outgassing from fuel systems, life support equipment, and astronaut activities rather than representing the pristine lunar atmosphere. More recent measurements from orbital missions paint a clearer picture of natural atmospheric processes. The Lunar Atmosphere and Dust Environment Explorer, which orbited the Moon from 2013 to 2014, carried instruments specifically designed to study the tenuous atmosphere without contamination from spacecraft operations. These measurements confirm that the exosphere contains primarily noble gases, alkali metals, and trace quantities of water vapor, with total mass estimated at approximately 25,000 kilograms, roughly equivalent to a large truck. The structure of the lunar atmosphere defies terrestrial intuition about how gases behave. On Earth, frequent molecular collisions create a well-mixed atmosphere with distinct layers defined by temperature and pressure gradients. The lunar exosphere lacks sufficient density for intermolecular collisions, so each atom or molecule follows an independent ballistic trajectory determined by its initial velocity and the Moon's gravitational field. Fast-moving particles can travel hundreds of kilometers above the surface before falling back, while slower ones follow suborbital arcs that return them to the surface within hours. Seasonal variations in atmospheric density reflect the complex interplay between source and loss processes. During lunar day, micrometeorite impacts and thermal desorption enhance atmospheric production, but high surface temperatures also increase escape rates as atoms acquire thermal velocities approaching escape velocity. Lunar night reduces both production and loss rates, but the balance shifts differently for various atmospheric components depending on their masses and chemical properties. The Moon's weak gravitational field, only 1/6 that of Earth, makes atmospheric retention extremely difficult. The escape velocity from the lunar surface is 2.4 kilometers per second, low enough that thermal motion alone can provide sufficient energy for atmospheric loss. Any molecule or atom that acquires a velocity exceeding this threshold through impacts, solar heating, or solar wind interactions will escape to interplanetary space unless it first collides with the surface or another atmospheric particle. Magnetospheric interactions add complexity to atmospheric dynamics when the Moon passes through Earth's magnetotail. During these periods, which occur for approximately 6 days each month, the lunar surface is partially shielded from solar wind bombardment, reducing sputtering rates and altering the balance between atmospheric production and loss. Some researchers suggest that these magnetotail passages may allow the atmosphere to become slightly denser due to reduced escape rates, though the effect remains difficult to measure given the extremely low baseline densities. Computer models of exospheric evolution must account for the three-dimensional structure of gas motion around an airless body. Unlike planetary atmospheres, where hydrostatic equilibrium creates well-defined pressure and density profiles, the lunar exosphere exhibits complex spatial variations driven by surface temperature differences, local gravitational anomalies, and the ballistic trajectories of individual particles. Some models predict that the atmosphere is denser on the night side, where cooler temperatures reduce escape rates, while others suggest day-side enhancement due to increased production from impacts and desorption. The practical implications of the lunar atmosphere become significant for certain types of space operations. Although far too thin to provide aerodynamic drag on orbiting spacecraft, the exosphere can affect sensitive scientific instruments designed to detect trace gases or measure the local space environment. Contamination from spacecraft outgassing can overwhelm the weak natural atmospheric signals, requiring careful operational procedures and instrument design to obtain meaningful measurements. Future lunar missions may inadvertently alter the natural atmospheric composition through their activities. Rocket exhaust, equipment outgassing, and dust kicked up by surface operations can temporarily increase local atmospheric densities by orders of magnitude. The Apollo missions demonstrated that human activities produce detectable atmospheric perturbations that persist for months after crew departure. Large-scale lunar development could create a permanently enhanced atmosphere around regions of intensive activity. Studies of the lunar atmosphere also provide insights into atmospheric processes on other airless bodies throughout the solar system. Mercury, many asteroids, and some moons of the outer planets possess similar exospheric envelopes generated by the same fundamental processes of impact vaporization, sputtering, and thermal desorption. Understanding these mechanisms in the relatively accessible lunar environment helps scientists interpret observations from more distant worlds where direct measurements remain challenging. Only took billions of years of gentle erosion to create this whisper-thin envelope, molecule by molecule, impact by impact, building an atmosphere so sparse that its total mass equals that of a few large boulders, yet technically qualifying as the gaseous shell that wraps the moon in its nearly imperceptible embrace. Deep within the moon's interior, rock fractures with the slow precision of a mechanical clock. These moonquakes occur monthly, triggered by Earth's gravitational pull on a cooling interior that contracts and cracks as temperatures gradually decline across geological time. Unlike the chaotic, unpredictable earthquakes that result from plate tectonics and active volcanism, lunar seismic activity follows patterns as regular as tides, reflecting the moon's simpler internal structure and the absence of the complex geological processes that drive terrestrial seismicity. The moon rings like a bell when struck, vibrating for hours with seismic waves that traverse the interior and reveal details about the satellite's composition and thermal state. The Apollo Passive Seismic Experiment, deployed during missions 12, 14, 15, and 16, provided humanity's first direct measurements of lunar seismic activity. 4 seismometer stations operated on the moon's near side from 1969 to 1977, recording thousands of moonquakes and meteoroid impacts with sensitivity exceeding that of most terrestrial seismic networks. The instruments detected vibrations so faint that they would be overwhelmed by background noise on Earth. The rumble of traffic, wind in trees, or waves breaking on distant shores. In the moon's perfect silence, seismometers could register the impact of meteoroids smaller than golf balls striking the surface hundreds of kilometers away. The seismic data revealed 4 distinct types of moonquakes, each with characteristic signatures that reflect different physical processes. Deep moonquakes occur 700 to 1 to 200 kilometers below the surface, near the boundary between the moon's rigid lithosphere and its partially molten interior. These events cluster around 300 specific source regions, each producing earthquakes with remarkable regularity at monthly intervals. The periodicity matches Earth's orbital motion around the Sun, suggesting that tidal forces generated by the changing gravitational geometry of the Earth-Moon-Sun system trigger fracturing in zones weakened by previous seismic activity. Shallow moonquakes occurring within 200 kilometers of the surface, generate the largest seismic signals recorded by the Apollo network. These rare events, numbering fewer than 30 during 8 years of monitoring, release energies equivalent to terrestrial earthquakes of magnitude 5 to 6. Their shallow depth and high stress drop the amount of stress released during rupture, suggests that they result from the brittle failure of highly fractured rocks in the Moon's outer layers. Some shallow moonquakes may represent delayed collapse of structures weakened by ancient impact events, the lunar equivalent of aftershocks occurring millions of years after the original disturbance. Thermal moonquakes provide a third category of seismic activity, occurring as the lunar surface experiences extreme temperature changes during the transition from 2-week day to 2-week night. Surface temperatures swing from 120 degrees Celsius in sunlight to minus 170 degrees Celsius in shadow, causing rocks to expand and contract with sufficient stress to generate small fractures. These events cluster around sunrise and sunset at each seismic station, creating a daily pattern of minor seismic activity as thermal gradients propagate into the subsurface and stress accumulated during temperature cycling exceeds the strength of brittle materials. Impact-generated seismic signals represent the fourth type of moonquake, created when meteoroids strike the lunar surface at hypervelocities. Natural impacts occur continuously as the Moon sweeps through the debris of comets and asteroids, but most are too small to register on seismometers. The Apollo missions provided controlled sources by deliberately crashing spent rocket stages and lunar modules into the Moon's surface. These artificial impacts generated seismic waves with known source locations and timing, allowing scientists to use the signals to probe the Moon's internal structure through seismic tomography. The artificial impacts revealed one of the most surprising characteristics of lunar seismology: the Moon's prolonged ringing. When the Apollo 12 lunar module impacted the surface in November 1969, seismic vibrations continued for over an hour, far longer than comparable signals would persist on Earth. This extended duration reflects the Moon's dry, highly fractured interior, which lacks the fluids and plastic deformation mechanisms that quickly damp seismic waves in terrestrial rocks. The Moon behaves acoustically like a rigid, hollow shell rather than the partially molten, layered structure typical of terrestrial planets. Computer analysis of seismic wave travel times and amplitudes provided the first detailed model of the Moon's internal structure, P waves, which compress and extend rock in the direction of propagation, travel through the Moon at velocities indicating a differentiated interior with distinct layers of varying composition and physical state. S waves, which shake rock perpendicular to their direction of travel, reveal regions where rocks have fractured extensively or where partial melting has occurred. The absence of S-wave transmission through certain regions suggests the presence of molten or highly fractured zones that cannot support shear stresses. The seismic data indicate that the Moon possesses a small metallic core, perhaps 300 to 400 kilometers in radius, surrounded by a partially molten zone extending to depths of approximately 1,000 kilometers. Above this lies a rigid lithosphere that includes both the lunar crust and the uppermost portion of the mantle. The lithosphere's thickness, estimated at 1,000 to 1,200 kilometers, represents nearly half the Moon's radius and indicates that the satellite has cooled much more extensively than Earth, whose lithosphere extends only 100 to 200 kilometers below the surface. Deep moonquakes concentrate in specific source regions that appear to correlate with the gravitational anomalies called Mascons. This relationship suggests that the dense material beneath large impact basins creates stress concentrations in the surrounding rocks, zones of weakness where tidal forces can trigger seismic failure. The regular timing of deep moonquakes, with most source regions producing events every 27.3 days in sync with the lunar orbital period, demonstrates the precision with which tidal stresses operate on scales ranging from ocean tides to solid rock deformation. Modern reanalysis of Apollo seismic data using advanced computational techniques continues to refine understanding of lunar internal structure. Sophisticated algorithms can extract weak signals from background noise, revealing small moonquakes that were undetectable with 1970s analysis methods. These techniques suggest that lunar seismic activity may be more common than originally recognized, with hundreds of small events occurring annually rather than the dozens recorded in initial catalogs. The Moon's seismic characteristics have implications for future lunar exploration and development. The prolonged duration of seismic waves means that large impacts or artificial explosions could generate ground motion lasting hours across the entire near-side hemisphere. Surface facilities would need to account for these extended vibrations, particularly sensitive scientific instruments or precision manufacturing equipment. The regular timing of deep moonquakes provides predictable windows when seismic background levels will be elevated, information useful for scheduling sensitive operations. Some researchers propose that future lunar missions could deploy modernized seismic networks to monitor ongoing geological activity and probe deeper into the Moon's interior structure. Current technology could detect much smaller moonquakes than the Apollo instruments recorded, potentially revealing details about core composition, mantle convection, and the thermal evolution of small planetary bodies. Such networks might also provide early warning of large impacts, useful for protecting surface installations from debris ejected by meteoroid collisions. The study of moonquakes also informs understanding of seismic processes on other airless bodies throughout the solar system. Many moons and asteroids likely experience similar tidal stresses and thermal cycling, generating seismic activity that could be detected by future robotic missions. The techniques developed for analyzing lunar seismic data provide templates for interpreting measurements from more distant worlds where direct sampling remains impossible. Only took 4 billion years of gradual cooling to create the current seismic regime, where stress accumulates slowly in cooling rocks until tidal forces provide the final trigger for fracture, releasing energy stored across decades of thermal contraction in brief moments of crystalline readjustment. At the Moon's center lies a puzzle wrapped in iron, a core so small it defies expectations of how planets form. This metallic heart comprises only 2% of the Moon's total mass, a proportion so tiny that early models of lunar formation struggle to explain its existence at all. Earth's core, by comparison, accounts for roughly 30% of our planet's mass, a substantial reservoir of iron and nickel that generates magnetic fields and drives geological processes. The Moon's diminutive core suggests a formation history fundamentally different from the standard planetary accretion that built the terrestrial worlds, supporting theories of violent origin through collision rather than gentle accumulation of cosmic dust and debris. The existence of a lunar core remained uncertain until the Apollo missions provided seismic data capable of probing the Moon's deepest interior. Seismic waves generated by artificial impacts and natural moonquakes travel at different velocities through rocks of varying composition and physical state. P waves, which compress and extend material in their direction of travel, pass through both solid and liquid regions but slow dramatically when encountering molten zones. S waves, which vibrate perpendicular to their propagation direction, cannot travel through liquids at all, creating shadow zones where these waves fail to appear at distant seismic stations. Analysis of seismic wave travel times revealed that both P waves and S waves reach the deepest parts of the Moon, indicating that the core region remains largely solid rather than molten. However, subtle variations in wave velocities and the partial attenuation of S waves suggested the presence of a small metallic region with properties intermediate between fully solid and completely liquid states. This evidence pointed to a core perhaps 300 to 400 kilometers in radius, tiny compared to the Moon's overall radius of 1,337 kilometers. Modern techniques for analyzing Apollo seismic data have refined estimates of core size and composition. Computer algorithms that can extract weak signals from noise have identified S-wave reflections from the core mantle boundary, providing more precise constraints on the depth and extent of the metallic region. These reanalyzed data suggest a solid inner core approximately 200 kilometers in radius, surrounded by a partially molten outer core extending to perhaps 400 kilometers from the Moon's center. The total iron content remains remarkably low, representing less than 5% of the Moon's mass compared to 30% for Earth. Laser ranging experiments provide independent evidence for the Moon's small core through precise measurements of the satellite's response to gravitational perturbations. As the Moon orbits Earth and experiences tidal forces from both Earth and Sun, its shape deforms slightly in response to these changing gravitational fields. The amount of deformation depends on the Moon's internal mass distribution, particularly the size and density of its core. Analysis of tiny variations in the Moon's distance and orientation, measured to millimeter precision by laser pulses reflected from retroreflectors placed by Apollo astronauts, indicates a core that accounts for less than 4% of the Moon's total mass. The Moon's small core poses challenges for understanding its magnetic history. Samples returned by Apollo missions contain evidence that lunar rocks were magnetized in ancient magnetic fields comparable in strength to Earth's current field. This paleomagnetic evidence suggests that the Moon possessed a substantial magnetic field between 3.6 and 4.2 billion years ago, requiring internal processes capable of generating and sustaining such fields over hundreds of millions of years. However, the Moon's tiny core appears insufficient to drive the convective motions necessary for magnetic field generation through dynamo processes. Several theories attempt to reconcile the paleomagnetic evidence with the Moon's small core. One possibility involves episodic core convection driven by the gradual cooling and crystallization of an initially molten interior. As the Moon cooled after its formation, the release of latent heat during core crystallization might have powered temporary convective motions capable of generating magnetic fields. This process would operate intermittently rather than continuously, potentially explaining why lunar magnetic signatures appear in some rock samples but not others. Another explanation involves magnetic field amplification through impact events. Large asteroid or comet impacts can generate intense, short-lived magnetic fields through the interaction of expanding plasma clouds with pre-existing weak fields. If the Moon possessed even a modest magnetic field from core convection, major impacts might have amplified this field to the strengths recorded in lunar rock samples. The timing of strong magnetic signatures coincides with the late heavy bombardment period, when large impacts occurred frequently throughout the inner solar system. The composition of the lunar core also differs from terrestrial expectations. Earth's core consists primarily of iron-nickel alloy with smaller quantities of lighter elements like sulfur, silicon, and carbon dissolved in the molten metal. Lunar core composition remains poorly constrained, but the low density inferred from seismic and gravitational data suggests significant quantities of lighter elements. Some models propose that the lunar core contains substantial amounts of sulfur, which would lower its density and reduce its melting temperature compared to pure iron-nickel alloy. The Moon's formation through giant impact provides a natural explanation for its small core. Computer simulations of the collision between Earth and the Mars-sized impactor Theia show that most of the iron from both bodies sinks toward Earth's center during the impact event, while the silicate material ejected into orbit contains relatively little metal. This preferential retention of iron by Earth and ejection of silicate-rich material explains both the Moon's low density and its small core, supporting the giant impact hypothesis over alternative formation mechanisms. Laboratory experiments with materials at the extreme pressures and temperatures relevant to planetary cores provide insights into the physical processes that might operate in the lunar interior. High-pressure studies reveal that iron-sulfur alloys remain partially molten at lower temperatures than pure iron, potentially allowing convective motions in the lunar core even after overall cooling has solidified the surrounding mantle. These experiments also show that sulfur-rich metallic liquids have electrical conductivity sufficient for magnetic field generation, though the field strengths would be weaker than those produced by pure iron cores. The Moon's core evolution continues today, though at rates imperceptible on human timescales. Radioactive decay of long-lived isotopes like potassium-40, uranium-238, and thorium-232 provides a steady heat source that slows the core's cooling and crystallization. However, the Moon's small size means that it loses heat to space much more rapidly than larger planets, preventing the sustained convective motions that maintain magnetic fields around Earth and other terrestrial worlds. The lunar core likely completed its transition from a convecting, magnetic field-generating state to a largely solid, magnetically quiet configuration within the first billion years of the Moon's existence. Future lunar missions may provide more direct constraints on core composition and structure. Seismic networks deployed across the lunar surface could detect core-reflected waves with greater precision than the limited Apollo seismic array achieved. Heat flow measurements would constrain the Moon's internal temperature distribution and the amount of radioactive heating still occurring in the deep interior. Analysis of additional rock samples, particularly those that preserve magnetic signatures from different time periods, could reveal details about the timing and intensity of ancient magnetic field generation. The study of the Moon's core also informs understanding of planetary formation and differentiation processes throughout the solar system. Many moons of the outer planets appear to have experienced similar core formation processes, though modified by their formation in the colder, outer regions where ice and organic compounds played larger roles. Comparing core sizes and compositions across different types of planetary bodies helps scientists understand how factors like formation location, timing, and impact history influence the internal structure of worlds throughout the galaxy. Only took a few million years after the giant impact for gravitational settling to separate the small amount of available iron from the predominantly silicate composition, creating a metallic heart so modest that its existence remained hidden until precision measurements revealed its subtle influence on seismic waves and orbital dynamics. Within the crystalline lattice of lunar rocks lies the ghost of an ancient magnetic field, preserved like a fossil in stone. These magnetic signatures, locked into the mineral structure billions of years ago, tell the story of a moon that once possessed the ability to generate magnetic fields rivaling those of Earth today. The evidence emerges from laboratory analysis of Apollo samples, which reveal that many lunar rocks carry remnant magnetizations far stronger than could be explained by the Moon's current magnetic environment. This paleomagnetic record suggests that between 3.6 and 2 billion years ago, the Moon maintained an active magnetic dynamo, powered by processes that have since fallen silent in the satellite's cooling interior. The discovery of lunar paleomagnetism surprised scientists who expected the Moon to be magnetically dead throughout its history. The satellite's small size and rapid cooling should have prevented the sustained convective motions necessary for magnetic field generation through dynamo processes. Yet, Apollo samples tell a different story. Basalt flows from the Lunar Maria, crystallized between 3.2 and 3.8 billion years ago. Preserved magnetic orientations indicating field strengths of 20 to 110 microtesla, comparable to Earth's current magnetic field of 50 microtesla. Highland samples, representing even older crustal materials, show evidence of magnetic fields that may have reached several hundred microtesla in strength. The mechanism that recorded these ancient magnetic signatures operates through the behavior of magnetic minerals during cooling. As molten rock crystallizes, iron-bearing minerals like magnetite and ilmenite form within the cooling mass. Above a critical temperature called the Curie point, thermal energy prevents these minerals from maintaining permanent magnetic orientations. However, as temperatures drop below the Curie point, the minerals become capable of recording the direction and intensity of any ambient magnetic field. Once locked in place, these magnetic orientations can persist for billions of years unless overprinted by later heating events or chemical alteration. Laboratory measurements of lunar sample magnetizations require sophisticated techniques to isolate the original magnetic signals from contamination acquired during sample collection, transport, and storage. Researchers use stepwise demagnetization procedures, gradually removing weak magnetic components through controlled heating or application of alternating magnetic fields. The remaining strong, stable components represent the original magnetic orientations acquired when the rocks first cooled on the lunar surface. Analysis of these stable directions reveals not only the strength of ancient lunar magnetic fields, but also their orientations relative to the Moon's rotation axis and orbital plane. The spatial distribution of magnetic signatures across the lunar surface provides clues to the source and configuration of ancient magnetic fields. Some Apollo samples show magnetic orientations that align with dipolar field configurations, similar to Earth's current magnetic field, with north and south magnetic poles roughly aligned with the rotation axis. Other samples preserve magnetic directions that suggest more complex field geometries, possibly indicating multiple magnetic poles or rapidly changing field orientations. The diversity of magnetic signatures may reflect temporal variations in dynamo intensity and configuration over the hundreds of millions of years when the lunar magnetic field remained active. Orbital magnetic field measurements provide additional evidence for the Moon's magnetic past. The Lunar Prospector and subsequent missions have mapped weak magnetic anomalies across the lunar surface, regions where the crustal rocks retain sufficient magnetization to create detectable perturbations in the local magnetic environment. These magnetic anomalies cluster in certain regions, particularly antipodal to large impact basins like Mare Imbrium and Mare Orientale. The antipodal concentration suggests that basin-forming impacts may have played a role in either creating or preserving strong crustal magnetizations. The timing of lunar magnetic field generation coincides with several important periods in early solar system history. The strongest magnetic signatures appear in samples dated to the late heavy bombardment, when large impacts frequently struck the inner planets and their satellites. Some researchers propose that major impacts provided the energy necessary to sustain core convection and magnetic field generation through mechanisms involving impact-induced heating, core crystallization, or temporary disruption of thermal boundary layers. The correlation between impact frequency and magnetic field strength suggests a causal relationship between bombardment and dynamo activity. Computer simulations of dynamo processes in small planetary bodies reveal the challenges facing magnetic field generation in the Moon's tiny core. Convective motions require a delicate balance between heat sources and cooling rates, with convection velocities sufficient to organize fluid motion into the spiral patterns necessary for magnetic field amplification. The moon's rapid cooling after formation should have quenched core convection within tens of millions of years, far too quickly to explain magnetic signatures that persist for hundreds of millions of years in the paleomagnetic record. One proposed solution involves precession-driven dynamos, where gravitational torques from Earth cause the moon's solid mantle to wobble relative to its liquid core. This relative motion could drive convective flows in the core fluid even after thermal convection has ceased, potentially sustaining magnetic field generation for extended periods. However, the strength and stability of precession-driven fields remain uncertain, and the mechanism may not produce field intensities comparable to those recorded in lunar samples. Another explanation focuses on the role of core crystallization in driving late-stage convection. As the lunar core cooled and began to solidize from the inside out, the release of latent heat and the expulsion of light elements from the growing solid inner core could have powered convective motions in the remaining liquid. This crystallization-driven convection operates efficiently in planetary cores and could sustain magnetic fields for hundreds of millions of years, depending on core composition and cooling rates. Impact-generated magnetic fields provide an alternative to internal dynamo processes for explaining some paleomagnetic signatures. Large meteoroid impacts create expanding clouds of ionized gas that can interact with existing weak magnetic fields to produce temporary field amplifications lasting hours to days. If the moon possessed even a weak magnetic field from other sources, major impacts could have amplified this field to the strengths recorded in crustal rocks. The timing and distribution of strong magnetic signatures support this impact amplification hypothesis. Laboratory experiments with materials at high pressure and temperature help constrain the conditions under which lunar dynamo processes might have operated. Studies of iron-sulfur alloys relevant to core composition reveal the electrical conductivities and convective properties necessary for magnetic field generation. These experiments suggest that the lunar core, despite its small size, could have generated magnetic fields comparable to those recorded in Apollo samples if appropriate conditions existed for sustained convection. The gradual decay of the lunar magnetic field appears to have occurred over several 100 million years, with the strongest signatures dating to the earliest preserved rocks and progressively weaker magnetizations in younger materials. By 2 billion years ago, when the latest mare basalts crystallized, magnetic field strength had decreased to levels barely detectable in rock samples. This decline probably reflects the natural cooling and solidification of the lunar core, which eliminated the fluid motions necessary for continued dynamo operation. The absence of a strong magnetic field today leaves the moon vulnerable to erosion by the solar wind. The stream of charged particles continuously flowing from the sun, without magnetic shielding. Solar wind particles strike the lunar surface directly, gradually sputtering away atoms from surface minerals and contributing to the formation of the tenuous lunar atmosphere. The contrast between past magnetic protection and current vulnerability illustrates how dramatically the moon's magnetic environment has changed over geological time. Modern lunar missions continue to refine understanding of the moon's magnetic history through increasingly sophisticated measurements of crustal magnetic anomalies and their relationship to geological features. High-resolution magnetic maps reveal complex patterns of magnetization that reflect the interplay between impact processes, volcanic activity, and the timing of magnetic field generation and decay. These observations provide constraints on models of dynamo operation and help distinguish between different mechanisms proposed for lunar magnetic field generation. Future sample return missions may provide additional paleomagnetic records from regions not visited by Apollo astronauts. Samples from the lunar far side, the polar regions, and locations with different geological histories could reveal whether magnetic field generation was a global phenomenon or restricted to certain regions and time periods. Such samples would also help constrain the orientation and stability of ancient magnetic fields relative to the Moon's rotation and orbital configuration. Only took 500 million years for the lunar dynamo to wind down. Its magnetic ghost now preserved in scattered rock samples that carry the memory of a time when the Moon possessed invisible lines of force extending into space, shielding the surface from solar wind and creating the conditions necessary to record its own magnetic history in the cooling minerals of an ancient world. In the vast cosmos, where distances span millions of kilometers and celestial bodies differ in size by orders of magnitude, a remarkable coincidence unfolds in Earth's sky. The Moon and Sun appear nearly identical in angular size when viewed from our planet's surface, a cosmic alignment that enables the spectacular phenomenon of total solar eclipses. The Moon's average angular diameter measures 31.1 arc minutes, while the Sun spans 32.0 arc minutes, creating an overlap so precise that lunar eclipses can completely obscure the solar disk while revealing the Sun's ethereal corona. This extraordinary correspondence has no accepted scientific explanation and represents one of the most puzzling coincidences in the solar system. The mathematical precision of this alignment becomes apparent through simple calculations. The Moon's diameter measures 3,174 kilometers, while the Sun spans 39 million kilometers, roughly 400 times larger. Remarkably, the Sun also lies approximately 400 times farther from Earth than the Moon, creating the geometric conditions necessary for apparent size matching. The Moon orbits at an average distance of 384,400 kilometers from Earth, while the Sun maintains an average distance of 149.6 million kilometers. These ratios fluctuate slightly due to orbital variations, but remain sufficiently close to enable total solar eclipses under favorable geometric conditions. The temporal nature of this coincidence adds to its mystery. The Moon gradually recedes from Earth at 3.8 centimeters per year due to tidal friction, slowly shrinking in apparent size as viewed from our planet's surface. In the distant past, when the Moon orbited closer to Earth, it appeared larger in the sky and would have completely obscured the Sun during eclipses, hiding the corona entirely. In the far future, when the Moon has retreated significantly farther from Earth, it will appear too small to cover the solar disk completely, ending the era of total solar eclipses forever. Current estimates suggest that total solar eclipses as we experience them today represent a temporary phenomenon lasting roughly 1 billion years out of the Moon's 4.5 billion year existence. Early in lunar history, when the satellite orbited perhaps 20,000 kilometers from Earth, it would have appeared 16 times larger than today, creating eclipses that lasted hours rather than minutes and blocked not only the Sun but also significant portions of the surrounding sky. Conversely, in approximately 600 million years, the Moon will appear too small to completely cover the Sun, producing only annular eclipses where a ring of sunlight remains visible around the lunar silhouette. The mechanics of solar eclipses depend on the precise alignment of Sun, Moon, and Earth, with the Moon's shadow falling across Earth's surface along a narrow path typically 100 to 300 kilometers wide. The shadow consists of two parts: the umbra, where the Moon completely blocks the Sun, and the penumbra, where only partial obscuration occurs. Observers within the umbral path experience totality, with darkness lasting from seconds to a maximum of about 7 minutes, depending on the relative distances and speeds of the celestial bodies involved. The apparent size match between Moon and Sun enables unique scientific observations impossible during other astronomical events. During totality, The moon blocks the bright solar photosphere while allowing the much fainter corona to become visible, revealing the sun's extended atmosphere and its complex magnetic field structures. Historical solar eclipse observations led to discoveries including the solar corona's extreme temperature, the existence of coronal mass ejections, and the confirmation of Einstein's general relativity through measurements of starlight deflection near the sun's limb. The rarity and geographic specificity of total solar eclipses has inspired human cultures throughout history. Any given location on Earth's surface experiences totality roughly once every 375 years on average, though the actual intervals vary widely due to the complex mechanics of orbital motion. Some regions may wait over 1,000 years between total eclipses, while others experience multiple events within decades. This temporal and spatial unpredictability has made total solar eclipses among the most sought-after natural phenomena, driving eclipse chasers to remote locations worldwide. Ancient civilizations interpreted solar eclipses as supernatural events, often associating them with the intervention of gods or dragons consuming the sun. Chinese astronomers developed sufficiently accurate predictive models to forecast eclipses by the 8th century BCE, though the physical explanation for these events remained unknown until the development of modern astronomy. The apparent size correspondence between moon and sun was recognized as remarkable even by ancient observers, who noted that lunar eclipses seemed precisely calibrated to reveal the sun's hidden corona. Other planetary systems likely lack this precise apparent size matching. Most moons in our solar system appear either much smaller or much larger than the sun when viewed from their parent planets. Mars's tiny moons, Phobos and Deimos, appear as small dark spots crossing the solar disk rather than creating true eclipses. Jupiter's large moons cast shadows on the planet, but appear much smaller than the sun from Jupiter's cloud tops. Saturn's moon Titan could theoretically create solar eclipses from Saturn's surface, but the match would be far less precise than the Earth-Moon-Sun system. The statistical improbability of the apparent size coincidence has led some researchers to question whether it represents pure chance or hints at deeper physical principles. One hypothesis suggests that the moon's formation through giant impact naturally created initial conditions that would eventually lead to apparent size matching through the satellite's subsequent orbital evolution. However, computer simulations of giant impact scenarios show wide variations in initial lunar orbital distances and recession rates, making such fine-tuning unlikely through purely random processes. Another perspective focuses on observational selection effects related to the development of complex life and intelligent observers. Some researchers propose that the gravitational and tidal effects of a large moon may be necessary for maintaining stable climatic conditions suitable for complex biological evolution. If true, intelligent observers might naturally find themselves on planets with large moons, increasing the probability of apparent size coincidences. However, this anthropic explanation remains speculative and difficult to test given our limited knowledge of planetary systems and biological evolution elsewhere in the universe. The precision of the apparent size match varies with lunar distance due to the moon's elliptical orbit. At perigee, when the moon approaches closest to Earth, it appears approximately 14% larger than at apogee, its most distant point. Solar distance also varies due to Earth's elliptical orbit around the Sun, with the Sun appearing about 3% larger in January than in July. These orbital variations create a range of eclipse types, from total eclipses when the moon appears larger than the sun to annular eclipses when the reverse occurs. Modern eclipse predictions require sophisticated calculations accounting for the gravitational influences of all major solar system bodies. the effects of Earth's irregular shape and rotation, and the gradual changes in orbital parameters over time. Despite these complexities, astronomers can predict eclipse paths and durations with remarkable accuracy centuries into the future, demonstrating the fundamental regularity underlying apparently chaotic celestial mechanics. The study of ancient eclipse records provides insights into the long-term evolution of Earth's rotation and the Moon's orbit. Historical accounts of eclipses from Babylon, China, and medieval Europe, when compared with modern calculations, reveal systematic timing discrepancies that confirm the gradual slowing of Earth's rotation due to tidal friction. These observations provide independent verification of the Moon's ongoing recession and help constrain models of tidal evolution over geological timescales. The apparent size coincidence will remain one of the most remarkable features of our solar system for the duration of human civilization. Whether this represents pure chance, an inevitable consequence of physical processes, or evidence of deeper organizing principles, remains an open question in astronomy and philosophy. The phenomenon serves as a reminder that the universe contains patterns and relationships that challenge our understanding of probability, causation, and the nature of cosmic order. Only took 4.5 billion years of orbital evolution to achieve this temporary geometric precision, creating conditions that will persist for perhaps another billion years before the Moon's continued recession renders total solar eclipses impossible, ending forever this cosmic dance of shadows and light. The Moon's surface lies buried beneath a blanket of dust so fine it defies earthly comparison. This regolith, pulverized by billions of years of relentless bombardment, extends to depths of several meters across the Maria and tens of meters in the highland regions. Each grain represents the accumulated violence of hypervelocity impacts, as meteoroids ranging from microscopic particles to boulder-sized fragments have struck the airless surface at speeds of 10 to 70 kilometers per second. The resulting powder possesses properties that would seem impossible on Earth. Individual particles welded together by solar wind radiation, glass beads formed in moments of impact heating, and fragments of rock shocked into crystal structures that exist nowhere else in nature. The formation of lunar regolith operates through processes fundamentally different from terrestrial soil development on Earth. Weathering proceeds through chemical reactions involving water, oxygen, and organic acids that gradually decompose rock into clay minerals and dissolved compounds. The Moon lacks water, atmosphere, and biological processes, so mechanical fragmentation dominates. Each impact, no matter how small, chips away tiny fragments of rock and redistributes them across the surface. Over geological time, this space weathering has processed and reprocessed every grain of surface material multiple times, creating a layer of debris that records the solar system's bombardment history. The size distribution of regolith particles follows a mathematical relationship that reflects the fractal nature of impact fragmentation. Most grains measure between 10 and 100 micrometers in diameter, roughly the size of flour or talcum powder, though the distribution includes everything from submicron dust to centimeter-sized rock fragments. The finest particles, created by the most energetic impacts, can travel hundreds of kilometers from their source craters before settling to the surface. This global mixing means that samples collected at any location contain materials from across the entire lunar surface, creating a natural repository of planetary composition. Apollo astronauts encountered regolith properties that surprised mission planners and complicated surface operations. The powder clings to everything with electrostatic attraction, coating spacesuits, equipment, and even penetrating sealed containers through microscopic gaps. The fine particles lack the cohesion typical of terrestrial soils, creating a surface that behaves like loose sand despite its powder-like appearance. Footprints and rover tracks remain sharp and well-defined due to the absence of wind or water to blur their edges, preserving human traces that will persist for millions of years. Laboratory analysis of returned regolith samples revealed complex mineralogy created by impact processes. Glass spherules, formed when impact energy melts small quantities of target rock, comprise up to 20% of some samples. These spherules range from perfect spheres created during ballistic flight to irregular shapes that cooled more rapidly or experienced secondary impacts. Chemical analysis shows that the glass compositions reflect local bedrock, but also include exotic components from impacting meteoroids, providing a record of the projectiles that have struck the Moon throughout its history. Agglutinates represent another unique component of lunar regolith, formed when micrometeorite impacts weld together small rock and mineral fragments with impact glass. These particles, which have no terrestrial equivalent, comprise the majority of mature regolith and give the lunar surface its characteristic dark color and low reflectivity. The welding process occurs at temperatures of several thousand degrees Celsius during impacts lasting microseconds, creating composite particles that preserve a record of countless small impact events. The maturity of lunar regolith varies significantly across the surface, reflecting different exposure times to space weathering processes. Young surfaces, such as recent crater ejecta or lava flows, contain relatively little impact glass and few agglutinates, giving them higher reflectivity and lighter colors observable through telescopes. Mature surfaces, exposed to bombardment for hundreds of millions of years, appear darker due to the accumulation of impact glass and the gradual reduction of iron-bearing minerals by solar wind hydrogen. This maturation process provides a method for estimating the relative ages of lunar surface features. Soil mechanics experiments with lunar regolith samples reveal properties that would challenge engineering applications on the Moon's surface. The material has virtually no tensile strength when loose, yet can support substantial loads when confined. The lack of moisture and organic binding agents means that excavated regolith behaves like dry sand, requiring mechanical compaction or artificial binding agents to create stable structures. The fine particle size and electrostatic properties make the material extremely difficult to contain, with implications for life support systems and equipment maintenance during extended lunar missions. The depth of regolith varies dramatically across the lunar surface, reflecting differences in bombardment history and geological processes. Young maria, such as Mare Imbrium, have regolith layers only 2 to 8 meters thick, developed over the 3.2 billion years since the last major volcanic activity. Highland regions, exposed to bombardment for over 4 billion years, contain regolith extending 10 to 20 meters deep. Some ancient crater floors may have regolith deposits exceeding 100 meters in thickness, representing the accumulated debris from billions of years of impact gardening. Chemical analysis of regolith samples provides insights into solar wind interactions with the lunar surface. Hydrogen, helium, carbon, and nitrogen implanted by solar wind particles create concentration gradients in the uppermost millimeters of regolith grains. These solar wind components can be extracted through heating, potentially providing resources for future lunar missions. Helium-3, a rare isotope deposited by solar wind, has attracted attention as a potential fuel for fusion reactors, though the concentrations are extremely low and extraction would require processing enormous quantities of regolith. The distribution of regolith also preserves evidence of major impact events that occurred throughout lunar history. Rays of light-colored material extending hundreds of kilometers from young craters like Tycho and Copernicus consist of fresh regolith excavated from depth and deposited over older, space-weathered surfaces. These ray systems fade over time as space weathering darkens the fresh material, providing another method for estimating crater ages. The absence of ray systems around older craters indicates that space weathering erases such features within approximately 100 million years. Micrometeorite impact experiments conducted in laboratory settings help calibrate the rates of regolith formation and maturation. Researchers use particle accelerators to fire microscopic projectiles at rock samples at hypervelocities, simulating the conditions of space weathering on airless bodies. These experiments reveal that mature regolith properties develop over timescales of 10 to 100 million years for surfaces with typical micrometeorite flux rates. The results help interpret the maturation state of different lunar regions and predict similar processes on other airless bodies throughout the solar system. Remote sensing techniques allow scientists to map regolith properties across the entire lunar surface using data from orbital spacecraft. Thermal infrared measurements reveal differences in particle size and rock abundance, as larger fragments cool more slowly than fine-grained regolith during lunar night. Radar observations penetrate several meters into the regolith, detecting buried rocks and variations in density that reflect local geological history. These techniques provide global context for the detailed measurements available from Apollo sample sites. The study of lunar regolith also informs understanding of space weathering processes on asteroids, Mercury, and the moons of outer planets. Similar mechanical fragmentation and solar wind interactions operate on all airless bodies, though the details depend on factors like surface composition, bombardment rates, and distance from the Sun. Spacecraft observations of asteroids show evidence of regolith layers and space weathering effects comparable to those documented on the Moon, supporting the universality of these processes throughout the solar system. Future lunar missions will need to account for regolith properties in spacecraft design, surface operations, and resource utilization planning. The material's tendency to adhere to surfaces and penetrate equipment requires careful attention to sealing and cleaning systems. However, regolith also represents a valuable resource for construction materials, radiation shielding, and extraction of solar wind-implanted volatiles. Understanding its properties and distribution will be essential for sustainable lunar exploration and development. Only took 4 billion years of patient grinding to create this global blanket of debris. Grain by grain, impact by impact, building a surface layer that preserves the memory of every collision while slowly erasing the evidence through continued bombardment and mixing, creating an archive of solar system history written in microscopic fragments of pulverized stone. The Moon emerges from its formation conspicuously empty of the materials that define planetary birth. Water-bearing minerals, which comprise substantial portions of meteorites and terrestrial rocks, appear almost entirely absent from lunar samples. Light elements like hydrogen, carbon, nitrogen, and noble gases occur in concentrations thousands of times lower than those found in primitive meteorites or Earth's mantle. This depletion of volatile components suggests that the Moon formed under conditions so extreme that temperatures vaporized the very substances essential to planetary formation, supporting theories of origin through catastrophic collision rather than the gentle accumulation processes that built most solar system bodies. The evidence for volatile depletion emerges from detailed chemical analysis of Apollo samples returned between 1969 and 1972. Laboratory measurements reveal that lunar rocks contain virtually no water locked within their crystal structures, unlike terrestrial rocks which typically contain several hundred to several thousand parts per million of water in hydroxyl groups bonded to minerals. Highland anorthosites, representing the Moon's primordial crust, show water concentrations below detection limits of most analytical techniques. Even mere basalts, formed through partial melting of the lunar interior billions of years after formation, contain water levels barely measurable with the most sensitive instruments. The absence extends beyond water to encompass the entire spectrum of volatile elements. Potassium, a moderately volatile alkali metal, occurs in lunar rocks at concentrations roughly 1/10 those typical of terrestrial basalts or primitive meteorites, lead, zinc, bismuth, and other elements that vaporize at moderate temperatures show similar depletions. The pattern becomes more extreme for highly volatile elements. Carbon concentrations in lunar samples rarely exceed a few parts per million, while nitrogen occurs at levels so low that contamination from terrestrial atmosphere during sample handling presents measurement challenges. Isotopic analysis provides additional evidence for high-temperature formation processes. Elements that fractionate significantly during evaporation and condensation processes show isotopic signatures consistent with extensive volatile loss. Potassium isotopes in lunar samples are systematically heavier than those in terrestrial rocks, indicating preferential loss of the lighter isotope during high-temperature processing. Silicon isotopes show similar fractionation patterns, suggesting that even moderately refractory elements experienced some degree of evaporative loss during lunar formation. The Moon's volatile depletion contrasts sharply with the composition of primitive meteorites, which preserve the original chemical inventory of the solar nebula from which planets formed. Carbonaceous chondrites contain up to 10% water by weight, along with substantial quantities of organic compounds, noble gases, and other volatile materials. If the Moon had formed through standard accretionary processes, it should retain at least some fraction of these primitive components. The near-complete absence of volatiles indicates formation through processes that operated at temperatures high enough to vaporize water, carbon compounds, and other materials essential to early planetary composition. Computer simulations of the giant impact that formed the Moon reveal the extreme thermal conditions that could account for volatile loss. When the Mars-sized impactor Theia struck early Earth, the collision generated temperatures exceeding 4,000 degrees Celsius in the impact region, hot enough to vaporize silicate rocks and convert solid matter into plasma. The debris disk ejected by this collision would have consisted primarily of vapor and molten droplets, creating an environment where volatile materials could escape to space before condensing into the solid Moon. The timing of volatile loss provides constraints on lunar formation mechanisms. If the depletion occurred after solid Moon formation through subsequent heating events, isotopic fractionation patterns would differ from those observed in Apollo samples. The systematic nature of the volatile depletion and its correlation with element volatility suggests that loss occurred during the formation process itself. When the proto-lunar material existed as vapor and liquid rather than solid rock, this timing supports formation through giant impact over alternative mechanisms like capture or fission. Laboratory experiments simulating high-temperature evaporation of silicate materials help quantify the conditions required for observed volatile depletion patterns. Researchers heat rock samples to temperatures exceeding 2,000 degrees Celsius in vacuum chambers and analyze the composition of remaining solid residues. These experiments demonstrate that extensive volatile loss requires not only high temperatures but also low pressures that allow vapor to escape rather than recondensing. The combination of high temperature and low pressure in the post-impact debris disk provides ideal conditions for volatile depletion. The Moon's volatile depletion has implications for understanding the source materials that contributed to its formation. Analysis of oxygen isotopes in lunar samples reveals nearly identical ratios to those in Earth's mantle, indicating that both bodies formed from the same reservoir of source materials. However, The extreme volatile depletion in lunar rocks suggests that these materials underwent extensive processing that did not affect Earth's bulk composition. This asymmetric processing supports models where the Moon formed primarily from Earth's outer layers, which were more extensively vaporized during the giant impact. Some volatile elements show partial retention in lunar samples, providing insights into the thermal history of Moon formation. Sulfur, which has intermediate volatility between refractory and highly volatile elements, occurs in lunar rocks at levels roughly half those typical of terrestrial basalts. This partial depletion suggests that sulfur-bearing compounds experienced some loss during formation but retained higher concentrations than more volatile species. The pattern of partial retention helps constrain the temperature and pressure conditions during lunar accretion. Recent discoveries of trace water in lunar samples have refined understanding of volatile depletion processes. Advanced analytical techniques can now detect water concentrations as low as a few parts per million in mineral inclusions within lunar rocks. Some of this water may represent original lunar materials that escaped complete dehydration, while other water signatures likely result from solar wind hydrogen interacting with oxygen-bearing minerals over geological time. Distinguishing between indigenous and secondary water sources remains an active area of research. The volatile depletion also affects the Moon's atmospheric evolution and surface processes. The absence of water-bearing minerals means that lunar rocks cannot generate substantial atmospheric water vapor through thermal decomposition or impact heating. This lack of internal volatile sources helps explain why the Moon maintains only an extremely tenuous exosphere despite billions of years of outgassing that would have created substantial atmospheres around more volatile rich bodies. The Moon's atmospheric composition reflects primarily external sources like solar wind and micrometeorite impacts rather than internal degassing. Comparative planetology reveals that volatile depletion is not universal among lunar-sized bodies in the solar system. Many moons of the outer planets contain substantial quantities of water ice and other volatile compounds, reflecting formation in colder regions where these materials remain stable. Even Mercury, despite its proximity to the Sun, appears to contain more volatile elements than the Moon, suggesting that formation location alone cannot account for the Moon's extreme depletion. The combination of high formation temperatures and efficient volatile escape required special circumstances that may be relatively rare in planetary formation. The study of lunar volatile depletion also provides insights into the early thermal evolution of the Earth-Moon system. The energy released during the giant impact would have created a molten surface layer on Earth extending hundreds of kilometers deep, potentially driving off substantial quantities of Earth's original volatile inventory as well. However, Earth's larger mass and stronger gravitational field would have enabled more efficient retention and recapture of volatiles compared to the smaller Moon. This differential volatile retention may explain some of the compositional differences between Earth and Moon, despite their similar oxygen isotope signatures. Future sample return missions to unexplored lunar regions may provide additional constraints on volatile depletion patterns and their relationship to local geological processes. Samples from permanently shadowed polar regions, volcanic glass deposits, and ancient impact melt sheets could reveal whether any lunar environments preserved higher volatile concentrations or whether depletion was globally uniform. Such measurements would help distinguish between different models of volatile loss and provide insights into the heterogeneity of formation conditions across the early Moon. Only took the few hours duration of the giant impact to strip away billions of years' worth of accumulated volatile materials, creating a world so thoroughly dehydrated that discovering trace amounts of water became one of the most significant achievements of modern lunar science, revealing the extreme conditions under which planetary satellites can form when violence rather than gentle accumulation shapes their birth. The Moon continues its ancient journey away from Earth, retreating at the pace of growing fingernails while carrying within its battered surface the unresolved mysteries of planetary formation. Each month, laser pulses fired from observatories around the world confirm the satellite's steady recession, measuring distances to the millimeter and documenting the gradual weakening of gravitational bonds that have linked these two worlds for over 4 billion years. In approximately 5 billion years, when the Sun begins its transformation into a red giant star, the Moon will orbit at perhaps twice its current distance, appearing as a distant point of light in Earth's sky rather than the substantial disk that has guided human navigation and inspired countless generations to wonder about the cosmos beyond our world. The scientific puzzles surrounding lunar origin and evolution persist despite decades of detailed study and increasingly sophisticated analytical techniques. The giant impact hypothesis explains many observed characteristics of the Earth-Moon system, yet computer simulations still struggle to reproduce all aspects of the satellite's composition, angular momentum, and orbital properties simultaneously. The isotopic similarities between Earth and Moon rocks suggest a common origin, but the Moon's severe depletion in volatile elements indicates formation processes more extreme than standard planetary accretion. These apparent contradictions keep lunar scientists engaged in ongoing debates about the precise mechanisms that created our cosmic companion. Future missions to the Moon promise to address some of these lingering questions through direct sampling of previously unexplored regions. The lunar far side, permanently hidden from Earth's view, may preserve different geological signatures that could reveal asymmetries in the Moon's formation and early evolution. Polar regions containing water ice deposits offer opportunities to study both the sources of lunar volatiles and the processes that concentrate them in permanently shadowed locations. Deep drilling into the lunar interior could provide samples of materials that have remained unaltered since the Moon's formation, potentially preserving chemical and isotopic signatures that would resolve debates about impact versus accretion origin scenarios. The Moon's gravitational influence on Earth extends far beyond the familiar cycle of ocean tides. The satellite's presence has gradually slowed Earth's rotation from perhaps 6 hours per day in the early solar system to the current 24-hour cycle, fundamentally altering the planet's climate and atmospheric dynamics. The Moon also stabilizes Earth's axial tilt, preventing the chaotic oscillations that would otherwise result from gravitational perturbations by other planets. This stabilizing influence may have been crucial for maintaining the consistent climatic conditions that enabled the evolution of complex life over geological timescales. As the Moon retreats, its moderating influence on Earth's rotation and axial stability will gradually diminish. The lengthening of Earth's day will continue, though at an ever-decreasing rate as tidal forces weaken with distance. Eventually, billions of years in the future, Earth and Moon will become mutually tidally locked, with the same hemisphere of each body always facing the other. At that point, the Moon will appear stationary in the sky for observers on one side of Earth, while remaining forever invisible from the opposite hemisphere. The familiar cycle of lunar phases will end, replaced by a Moon that maintains constant illumination relative to Earth's surface. The Moon's role as a natural laboratory for understanding planetary processes extends throughout the solar system. Its airless surface and geological stability preserve impact crater records that have been erased from more geologically active worlds. The lunar sample collection provides ground truth for interpreting remote sensing observations of other moons and asteroids. Techniques developed for analyzing lunar rocks and understanding lunar processes inform studies of planetary formation and evolution throughout the galaxy. The Moon serves as humanity's most accessible example of a differentiated, cratered world that has preserved evidence of early solar system conditions. Technological applications continue to emerge from lunar research, ranging from improved understanding of materials science under extreme conditions to insights into resource utilization on airless bodies. The development of techniques for extracting water from permanently shadowed regolith, processing lunar soil for construction materials, and operating equipment in the harsh lunar environment will prove essential for future space exploration missions to asteroids, Mars, and the moons of outer planets. The Moon provides an ideal testing ground for technologies and procedures that will enable sustained human presence throughout the solar system. The cultural and philosophical significance of the Moon transcends its scientific importance. For millennia, human societies have used lunar cycles to organize calendars, navigate across oceans, and mark the passage of seasons. The Moon appears in creation myths, religious traditions, and literary works across all cultures, representing humanity's earliest systematic observations of celestial mechanics. The Apollo missions demonstrated that humans could reach other worlds, fundamentally changing perspectives about Earth's place in the cosmic order and humanity's potential future among the stars. Educational and inspirational aspects of lunar science continue to engage new generations of scientists and explorers. The Moon's accessibility to amateur astronomers makes it an ideal target for citizen science projects and educational observations. Students can track lunar phases, observe surface features through small telescopes, and participate in research projects using data from current lunar missions. The combination of scientific accessibility and ongoing mystery makes the Moon an effective gateway for introducing concepts in planetary science, physics, and astronomy. International cooperation in lunar exploration has evolved from the competitive space race of the 1960s to collaborative scientific endeavors involving multiple nations and organizations. Current and planned lunar missions include participants from the United States, Europe, China, India, Japan, and other countries, reflecting the global nature of modern space science. Future human settlements on the Moon will likely involve international partnerships that share both the costs and benefits of lunar resource utilization and scientific discovery. Environmental considerations surrounding lunar exploration have gained attention as human activities on the Moon expand from brief visits to permanent installations. The preservation of scientifically important sites, management of space debris and contamination, and sustainable resource utilization practices will become increasingly important as lunar development proceeds. The Moon's geological record spans billions of years and represents an irreplaceable archive of solar system history that deserves protection even as it becomes humanity's first permanent foothold beyond Earth. The continuing mystery of lunar origin serves as a reminder that fundamental questions about planetary formation remain unresolved despite tremendous advances in observational capabilities and theoretical understanding. Each new measurement and sample analysis adds detail to our knowledge while often revealing unexpected complexities that require revised models and hypotheses. The Moon's formation may represent a relatively rare event in planetary systems, making our satellite a unique laboratory for understanding low-probability, high-impact processes that shape planetary evolution. The Moon drifts onward through space, carrying its burden of accumulated secrets toward an eventual destiny as a distant satellite of a dying star. Its scarred surface will continue to record the impact history of the inner solar system long after Earth's oceans have boiled away and its atmosphere has been stripped by an expanding sun. In that far future, the Moon may serve as humanity's longest-lasting monument, a world-sized museum preserving evidence of our species' first steps beyond the home planet and the scientific discoveries that revealed the violent processes through which worlds are born. Only took 4.5 billion years to create this cosmic puzzle. whose solutions remain tantalizingly beyond reach, despite the application of humanity's most sophisticated analytical techniques and theoretical models, ensuring that the moon will continue to inspire wonder and scientific inquiry for generations yet to come. The moon hangs in silence now, as it has for countless nights, carrying within its ancient rocks the memory of violence and the promise of mystery yet unsolved. Its face, scarred by eons of bombardment, reflects sunlight across the vacuum toward Earth with the same pale luminescence that guided our ancestors across dark seas and marked the passage of seasons before written history began. The satellite's slow retreat continues. Imperceptible to human awareness, yet measurable through the patient accumulation of laser-ranging data, each pulse of light that travels the quarter-million-mile journey to lunar retroreflectors and back confirms the gradual loosening of gravitational bonds that have held these two worlds in their cosmic dance since the solar system's violent youth. The moon moves away at the speed of growing fingernails, carrying its secrets toward a future when it will appear as merely a bright star in Earth's sky. In the permanently shadowed craters at the lunar poles, water ice waits in crystalline patience, preserved at temperatures colder than liquid nitrogen. This frozen archive of cometary impacts spans billions of years, grain by grain, impact by impact, accumulating in the only places where the geometry of crater walls and the moon's minimal axial tilt create refugia from the sun's destructive heat. The ice lies buried beneath layers of pulverized rock, a hidden ocean scattered across crater floors in quantities sufficient to sustain future human expeditions to this airless world. The moon's interior has long since cooled to geological silence. No tectonic plates shift across its surface, no volcanic eruptions release gases from depth, no magnetic field shields its surface from the solar wind. Only the subtle monthly rhythm of deep moonquakes marks the passage of time in the satellite's rocky heart, triggered by Earth's gravitational pull on zones of weakness that formed when the moon was young and its interior still molten from the energy of accretion and impact. The regolith continues its slow mixing, stirred by impacts too small to see but numerous enough to gradually overturn the surface layers across geological time. Each grain of lunar soil carries within its microscopic structure the record of hypervelocity collisions, solar wind bombardment, and the cosmic ray environment of interplanetary space. The finest particles, welded together by impact glass and darkened by eons of space weathering, create the moon's characteristic low reflectivity and somber coloration. Ancient magnetic signatures locked within highland rocks speak of a time when the moon possessed the ability to generate planetary magnetic fields rivaling those of Earth today. These paleomagnetic ghosts preserve the memory of internal processes that operated when the satellite was young, when its small core still convected and its surface still glowed with the heat of formation. The magnetic fields have long since faded, leaving only fossil traces in minerals that crystallized 4 billion years ago. The Mascons continue their invisible gravitational pull on everything that passes overhead. Dense concentrations of material buried beneath the circular maria, these mass anomalies represent frozen moments of cosmic violence, when impacts so energetic they excavated craters the size of small nations also punched through the lunar crust and allowed denser mantle material to rise toward the surface. The gravitational signatures will persist until the moon itself is destroyed, permanent monuments to the early solar system's chaos. The moon's synchronous rotation maintains the same familiar hemisphere facing Earth across every orbit, though tiny librations allow glimpses of terrain normally hidden beyond the limb. The gravitational lock that created this stability required millions of years to achieve through tidal friction, yet has remained stable for over 4 billion years since Euclidean testimony to the fundamental regularity underlying celestial mechanics. Soon, the moon will set beyond Earth's horizon for those observers lucky enough to witness its passage across star fields that have watched this dance for geological ages. Tomorrow night, it will rise again, perhaps a few arcseconds smaller than tonight due to its ongoing recession, carrying the same ancient mysteries toward whatever revelations await future generations of lunar explorers. The questions remain, suspended in the vacuum between worlds like the moon itself. How precisely did the giant impact unfold? What processes generated magnetic fields in such a small core? Why does the apparent size correspondence with the Sun exist at all? The answers lie locked within lunar rocks and buried beneath regolith layers, waiting for the instruments and techniques that will finally decode the satellite's formation story. In the deepest silence of space, the moon continues its patient orbit. Keeper of secrets, archive of violence, companion to Earth across the vast loneliness between the stars. Its scarred face reflects not only sunlight, but also the accumulated wonder of every human who has gazed upward and pondered the nature of worlds beyond our own. The ancient light falls gently across sleeping landscapes, marking time in the only units that matter on cosmic scales, the slow waltz of gravity, the patient erosion of impacts, the gradual cooling of worlds born in fire and destined for the cold perfection of empty space. Rest well beneath the moon's eternal gaze,